John Henry Schwarz is a titan of modern theoretical physics and the Harold Brown Professor of Theoretical Physics Emeritus at the California Institute of Technology. Recognized universally as one of the founding fathers of string theory, he demonstrated unparalleled intellectual courage by sustaining the field during the 1970s when it was largely abandoned by the scientific community. His visionary collaboration with Zoel Scherk fundamentally redefined the discipline by proposing that string theory was not merely a model of nuclear forces, but a unified quantum theory of gravity, predicting the existence of the graviton within a consistent mathematical framework. Swartz's most transformative contribution, the first superstring revolution of 1984, changed the course of physics history. Working with Michael Green, he provided the anomaly cancellation mechanism, demonstrating that superstring theory is free from the mathematical inconsistencies that plagued previous attempts at unification. This breakthrough established string theory as the premier candidate for a theory of everything, bridging quantum mechanics and general relativity. A recipient of the MacArthur Fellowship, the Dirac Medal, and the Breakthrough Prize in Fundamental Physics, Swartz's legacy is etched into the fundamental understanding of the dimensionality and structure of the universe. So, with this, I would like to invite Professor John Swartz to present his talk today. I'm very honored and happy to have you. So, thank you.
So I guess you've already told people that my title is String Theory in the 20th Century, a Personal Perspective. So let me tell you about all the crazy things I've been involved in. So I've been invited to give a personal account of the early history of string theory, which is the period from 1968 to 1985. The story I'll relate is quite unusual. A theory that was developed with the goal of describing the strong nuclear force turned out to be a unified theory of all fundamental forces, including gravity. The equations have many possible solutions, though we do not have unique predictions, but it is plausible that one of them can describe our universe. That remains, of course, to be demonstrated. My contributions have benefited greatly from excellent collaborators, primarily Andre Neveu, Joel Scherk, Larth Brink, and Michael Green. The string theory originated in an attempt to find a theory describing the strong nuclear force. So this work was in the early 1960s, and at that time, the only force for which there was a satisfactory quantum theory was the electromagnetic force. And that theory, called quantum electrodynamics, or QED for short, is a well-established quantum field theory of electrons and photons, which is today just as well regarded as it was back in the 1960s. Now, the goal of the high energy theory group in Berkeley when I was a graduate student a long time ago in the 1960s was to construct a theory of strongly interacting particles. And these particles are referred to as hadrons. The most familiar examples are the proton and the neutron. The correct theory of hadrons, named quantum thermodynamics, or QCD for short, was formulated in 1973, so later than the period I'm talking about now. And it is a quantum field theory of interacting quarks and gluons based on a Yang-Mills gauge group SU3. Now, for reasons I'll explain, it's fortunate that QCD wasn't discovered a few years earlier. Had it been discovered earlier, string theory might not have been developed for a very long time. Geoffrey Chew, who was my PhD advisor, proposed in the early 1960s that one could deduce the theory of hadrons from some general principles, including unitarity and analyticity of the S matrix. The S matrix is an infinite dimensional matrix that encodes all possible scattering processes. And unitarity ensures that all possible outcomes of an interaction have probabilities that are positive and add up to 1. Analyticity ensures that the dependence on the initial and final momenta is sufficiently smooth. Any singularities should have a physical interpretation. So to just give you a little sense of what the formulas looked like, let me just review some basic kinematics that I'm sure most of you already know. So we wish to determine a quantum mechanical amplitude, say for a relativistic reaction in which particles 1 and 2 collide and particles 3 and 4 emerge as a result. So representing the four momentum of the nth particle by p sub m sub mu. So mu runs over 0, 1, 2, 3. 0 represents energy, so p0 is energy, and 1, 2, 3 are the three components of the momentum. The conservation of energy and momentum in the process 1 plus 2 goes to 3 plus 4. It's just the equation, the obvious equation at the bottom. Now, setting the speed of light equal to 1, special relativity implies the dot product of or the square of a momentum given by the dot product, which has this minus sign corresponding to the signature that you have in relativity, is equal to the mass squared. In the case of zero momentum, this just says the energy is the mass, which is, of course, famous, Einstein's famous E equal mc squared. We've set c equal to 1 after all. So one also defines invariant variables, s, which is p1 plus p2 squared, t, which is p1 minus p3 squared, and u, which is p1 minus p4 squared. And in simple algebra, it tells you that the sum of st and u is the sum of the squares of the masses. So these three things are not independent. They have this relationship. So the goal was to determine a quantum mechanical scattering amplitude denoted A of S and T for a reaction in which particles 1 and 2 collide and give particles 3 and 4. So Q and Fauci in the early 60s proposed that in the case of hadrons, which is what we're talking about, particle exchanges provide the forces that are responsible for the particle's own existence. They found this reminiscent of a tale about a man who lifts himself up by his own bootstraps, which is of course absurd. But that analogy or example motivated this name for the conjecture. So this kind of a setup is quite different from conventional quantum field theory, because in conventional quantum field theory, one adds together the contributions of Feynman diagrams, which describe particle exchanges in all the different channels, S, T, and U. And this picture says that you can, if you just do it in one of them, you can deduce the others. So the big breakthrough really started with a formula that was written down in 1968 by Gabriele Veneziano. He discovered a formula that gives an explicit realization of the bootstrap principle and as well as other desirable properties. And a slightly simplified version of his formula is what I've written down here. So A is the amplitude we want. D is just a coupling constant, just a number. And B is Euler's beta function, which is given by some combination of gamma functions, also due to Euler, which, as you probably know, give a continuous interpolation for the notion of a factorial. The Regge trajectories, so these functions alpha are called Regge trajectories, and they're just linear functions. So alpha of s is the intercept alpha 0, and then it has a slope alpha prime s. So this extremely simple formula satisfies the bootstrap equations. And what that means is if you take this function and expand it in terms of the poles in the S channel, in the variable S, that's sum gives you back the entire function. But this formula has symmetry, so the same thing is true for the T channel. And to add, if you were to add those two contributions together, that would be double counting. So this is in contrast to conventional quantum field theory, where you would treat the poles in all the different channels separately. Soon thereafter, Virasoro proposed an alternative formula which looks a little more complicated, but it's not much. Just a different combination of these gamma functions. Uh, and amazingly, these two guessed formulas, just pulled out of the blue, turned out to be almost precisely the amplitudes for open string and closed string scattering that were soon found afterwards. In the modern interpretation, they correspond to gauge theory and gravity interactions, respectively. Now, the n-particle generalization of the Veneziano formula was found in 1969, just the next year, by several different groups simultaneously, more or less. And it's given by this little more complicated formula, but it's not too bad once you get into the stuff. Mu n is a measure which contains three delta functions, so that there are really only n minus 3 integrations. And restricts the variables such that the j plus first coordinate is larger than the j plus, because this has the appropriate step functions in it. So by a change of variables, this formula can be recast in a form in which the n-particle positions are at points on the boundary of a circular disk instead of an infinite line, which is the way it's written in the formula that I presented. So when you put them on when you make the change of variables to put them on a circle, then they have a specified cyclic ordering, which corresponds to these step functions I was discussing earlier. The particles in the previous formula only are required to belong to the adjoint representation of a gauge symmetry group, such as an orthogonal group or a symplectic group. And the complete tree approximation amplitude then takes the form of a sum of these n-particle amplitudes I've shown you with different permutations of the ordering of the particles and appropriate group theory coefficient, which are given by traces of products of matrices as the coefficients. Soon thereafter, Shapiro found a similar formula, which generalized Virazaro's formula, and it involves n minus 3 complex integrations. So the previous formula had dx's, this has d2z's. So this is twice as many integrals as the previous formula. And again, this measure involves some delta functions so that 3 of the z's can be fixed at specific positions. But now the remaining z's do not have an ordering. They can take arbitrary complex values. And so the particles described by this formula are singlets of the gauge symmetry groups. So they're invariant under the gauge symmetry. And this formula can be recast in an alternative way in which the n-particle positions are all at points on the surface of the two-dimensional sphere. But you can get that again by a change of variables. So the next development, this was really all quite amazing. This next development was that Fubini and Veneziano showed that these formulas have an internal consistency. Specifically, if you look at the poles in the formulas and take the residues of these poles, they factorize in terms of a well-defined spectrum of single particle states. And these single particle states can be described using an infinite number of harmonic oscillator operators. And these harmonic oscillator operators have two indices on them. One runs over the directions of space and time. So 1, 2, 3 are the spatial directions. U equals 0 refers to the time direction. And the index m goes over all the positive numbers. So there are an infinite number of these oscillators. And so these oscillators generate some enormous Fock space, which is roughly the spectrum of the theory. Now, there's one set of such oscillators in the Veneziano case and two sets in the Shapiro-Virasoro case. So what I've described here refers to the Veneziano case, and the Shapiro-Virasoro case would be a second set of oscillators that would have identical property to these. The fact that there is a consistent factorization with a well-defined spectrum of particles was the first indication that all these marvelous formulas were actually representing a theory and not just an intriguing collection of formulas. Because until this work of the Fubini and Veneziano, you had these beautiful integrals and everything, but they were just made up formulas. And now the factorization of the states with its oscillator description made it clear that these formulas actually came from an underlying theory. So the next question is, what is the theory? So in 1970, Nambu, Nielsen, and Susskind independently interpreted the formulas as arising from a theory of a relativistic string. So it's an open string. So these strings are infinitely thin. So they're really one-dimensional objects. And there are two possibilities. One is that they have two ends, and that's the kind of string called an open string, and it's relevant to the Veneziano case. And the alternative is you have what we call a closed string, which just means it's topologically a circle, but it can wiggle around arbitrarily. And it's the kind of string that the quantization leads to the Shapiro-Virasoro amplitudes. So these strings, when you think of their time evolution, sweep out two-dimensional world sheets in space-time. So the strings are one-dimensional. Their evolution gives a two-dimensional surface. Whoops, sorry. In space-time. So the open string particles attach to the boundary of a world sheet, and closed string particles attach to the interior of a world sheet. So having found the spectrum and tree approximation amplitudes of the string theory, it became possible to study quantum corrections or loop amplitudes. So these are completely analogous to what one does in ordinary quantum field theory, where we're using Feynman integrals, so it starts with tree amplitudes and then constructs quantum corrections given by diagrams that have loops. So do the same thing, except instead of instead of the particles being points that give lines in space-time, we have objects which are strings, which sweep out two-dimensional surfaces in space-time. Anyway, these are given by integrals. When you go to these loop amplitudes, the two-dimensional surfaces, which or stay in the closed string case, for example, where a sphere in the tree approximation will now be higher genus. So one loop case would be a torus, and then you would have more holes as you go to higher genus. And beyond one loop, the math gets really nasty. But at one loop, it's still manageable. So after graduating from Berkeley, I spent 6 years in Princeton before I moved to Caltech. And I followed all the developments I've been telling you about with great interest. But my first significant contribution was in 1970 in a paper that I co-authored with three people, David Gross, Andre Neveu, and Joël Scherk. So the four of us wrote a paper that studied open string one loop amplitudes. So the world sheet that we considered is topologically a cylinder with two circular boundaries. And there were two cases of interest that we considered. In the first case, all four particles in a 2-to-2 reaction are attached to one of the boundaries. And in the second case, two of them are attached to one boundary and two of them are attached to the other boundary. In the first case, the integral diverges, and this divergence can be removed by a well-understood non-controversial procedure previously introduced in a paper by Neveu and Scherk. So that case is okay. And it's the second case that turned out to be more profound. So in the second case, where you have two particles on each boundary, we were able to do the calculation, and we found that the amplitude contains branch points in the coordinate s equals p1 plus t2 squared. So and that the existence of these branch points violate the unitarity principle, which is absolutely sacred for making sense of this stuff as a quantum theory. So unless one could somehow eliminate these branch points, this could not be a consistent quantum theory. So this is a real serious problem. And for a while, at least, it looked like this whole business was dead. But a few months later, physicist who was at CERN at the time, Claude Lovelace, rescued the story, rescued the theory, by observing that these singularities would become poles, which would have a sensible physical interpretation rather than branch points. If we took this function alpha of s that I discussed earlier, it took the constant term alpha 0 to be 1, so that has to be 1. But so that's necessary, but even more dramatically, they found that it will only get poles if the dimension of space-time was 26. This was absolutely extraordinary because nobody working in this subject had ever considered any dimension other than 4 before this. And it seemed absolutely nuts. Why should the strong interactions want 26 dimensions? So Lovelace's discovery forced us to take extra dimensions of space, 22 of them in this case, seriously for the first time. But why should hadrons require extra dimensions? And why should the open spectrum, alpha 0 equal 1 implies that there's a massless spin 1 particle in the spectrum. Why should an open string spectrum have that property? So so even though we had what looked like a consistent theory, it certainly didn't look like the theory of hadrons that we wanted, both because of the space-time dimension and because there was a massless particle in the spectrum. So the new poles that Lovelace forced us to understand describe closed string intermediate states in the reaction 1 plus 2 goes to 3 plus 4. So when you have a cylindrical world sheet, there's two ways of thinking about it. It can be viewed either as a loop of open string. So you have a string with ends and you bring it around in a circle and that makes a cylinder. Or you can take a circle and propagate it for a certain finite distance. So you're taking a closed string, moving it for a certain distance, and that also gives a cylinder. And so the two different ways of thinking of it means that the process can be viewed as a loop of open string or just the propagation of a closed string. And so these poles that Lovelace found correspond to the closed string particles that you find at one loop in this way. So this alpha 0 equal 1 to equal 26 critical string theory has an infinite algebra of symmetries operators, L sub n, and goes over all the integers. And these symmetry operators are crucial for eliminating states with which would have negative norms, which is sort of like negative probabilities. And so the existence of these infinite algebra symmetries is absolutely crucial for getting a sensible spectrum in the sense that there are no ghosts with negative probability. So two different proofs of the no ghost theorem were found by Brouwer on the one hand and Goddard and Thorne on the other in 1972. So that was an important development too. Now, in January of 1971, Pierre Ramon introduced a string theory analog of the Dirac equation, which, as you probably know, is the relativistic wave equation for the electron. His proposal was that just as the string's momentum p mu can be viewed as the zero mode of a string density, capital P of sigma, the Dirac matrices, gamma mu, should be viewed also as the zero modes of densities, capital gamma of sigma. And so then he took the dot product, capital gamma dot P, and looked at all its Fourier modes in the usual way. And in particular, F sub 0 would give you the ordinary Dirac operator, gamma dot P, plus a bunch of other terms involving the oscillators associated with the non-zero modes of gamma and P. So the analog of the Dirac equation in this notation takes this very simple form. So I like to call this the Dirac-Ramond equation. The And he observed that the Virasoro algebra generalizes to a super Virasoro algebra that has odd elements f sub n in addition to the even elements ln that I mentioned earlier that generate the Virasoro algebra. The the f's sub being odd means they're fermionic, and if you want to combine two of them instead of having a commutator, you have an anti-commutator. The anti-commutator of two f's gives you an L in particular. So in March 1971, a couple months later, Andre Neveu and I introduced a second interacting bosonic string theory. And it's similar to the Ramon's fermionic theory, but the periodic density gamma mu of sigma is replaced by an anti-periodic one, which we called H. So here's the statement of what I mean by anti-periodic. So together with Charles Thorne, we showed next that the bosons that Neveu and I found and Ramon's fermions actually combine into a unified theory of bosons and fermions. And this was an early version of superstring theory, but there was much that still remained to be understood. I showed that the space-time dimension of the critical RNS string, by an analysis analogous to that of Lovelace, is 10 dimensions. So instead of 26 dimensions now, our second theory requires 10 dimensions. Goddard and Thorne independently showed that d equal 10 is the critical dimension for this theory. So my thinking at the time was that this is a step in the right direction, and maybe our next theory will have d equal 4. But that's not how the history played out. Later in 1971, Gervais and Sakita constructed a two-dimensional world sheet action for the string where the x's are just the bosonic coordinates, and then in the superstring we have the fermionic coordinate psi mu. And so this is sort of like a Dirac term, and this is sort of like a scalar term in a field theory. And they observed that this action has a symmetry where the x's can be rotated into size and the size can be rotated into x. It uses a fermionic symmetry. So this was actually the first explicit example in the literature of a theory with supersymmetry. And so here this is supersymmetry in two dimensions, relating the bosons x mu and the fermion psi mu. So this is the beginning of supersymmetry. So this result motivated Wesley Zumino to construct four-dimensional interacting supersymmetric field theories in 1973 and 74. And their work inspired the construction of possible supersymmetric extensions of the standard model. And that led to subsequent experimental searches at the LHC for supersymmetry particles, none of which have been discovered so far. Presumably they exist, but they're heavier than where the machine can probe so far. They might be very much heavier, in which case we'll never find them. I don't know. It makes sense that they continue looking. So let me tell you about the decline of string theory. So the success of QCD in 1973 eliminated the need to formulate a theory of hadrons based on strings. QCD was clearly the right theory. I knew it, everyone else knew it. String theory as a theory of hadrons had problems, an unrealistic dimension of space, 25 or 9, and the presence, which I didn't discuss earlier, of tachyons and massive particles. Tachyons are particles with negative mass squared, which means that which implies they would if you took them seriously, would be traveling faster than the speed of light. Of course, that's absurd, and so they shouldn't be that. Other exciting developments in this period, 73, 74, included the completion and acceptance of the standard model, as well as interest in studying supersymmetry, as I just mentioned, and grand unification, which is meant to relate the various forces that were known. Uh, and these were all very exciting topics. So it's not surprising, therefore, that string theory, which had been a thriving enterprise for several years, rapidly fell out of favor. Uh, the problem that it had set out to solve had been solved by a different method. End of story. Well, as it happens, as you know, I suppose, it's not the end of the story, because starting in 1973, Yonea in Japan interpreted the massless spin 2 state in the closed string spectrum in either 26 or 10 dimensions as a graviton, dimension, of course. With this identification and a theorem due to Weinberg, it was easy to show that the string theory agrees with general relativity in these dimensions, at least the energy is low compared to the string scale. Similarly, the massless spin 1 states in the open string spectrum could be interpreted as gauge theory particles. This had been shown earlier by Neveu and Scherk. So in 1974, Scherk spent a term at Caltech, collaborating with me, and we proposed to interpret string theory as a quantum theory of gravity unified with gauge theory forces. A potential, I don't like this phrase, but it's used a lot, the theory of everything, rather than as a theory of hadrons. And so this, it's hard to believe that this is more than 50 years ago. It doesn't feel that long. This new interpretation suggested that the string length scale is comparable to the Planck scale, which is 10 to the minus 33 centimeters, roughly, instead of the nuclear scale, which is roughly 10 to the minus 13 centimeters. So suddenly our strings shrank by 20 orders of magnitude, which is a rather dramatic rescaling, but the math was largely unaltered, which is fortunate. So at this time, I felt that I knew what I would be doing for the rest of my career, because I thought was pretty exciting, and that's pretty much the way things worked out. So this proposal had several obvious advantages. First of all, the existence of gravity is required by the theory. We didn't set out to build in gravity, it just happened to be there in these formulas. String theory has no ultraviolet divergences, which is a characteristic feature of ordinary quantum field theories. Sometimes these kinds of divergences can be handled by renormalization. That's the case in the standard model. And it's some theories that involve gravity. If you try to write down a quantum field theory for gravity, the ultraviolet divergences will not be renormalizable. They're too severe. So this is something that has gravity and it doesn't have ultraviolet divergences. So in a gravitational theory, extra dimensions can actually be a good thing. This was noted by Kaluza and Klein many years earlier, in the early part of the 20th century, quite shortly after Einstein's introduction of general relativity. The low energy 4D effective theory is determined by the details of the geometry of the compact extra dimensions. So that's an important thing. And in recent years, there's been a lot of work studying different possible geometries for the extra dimensions. The unification of gravity with forces described by Yang-Mills theories is automatic in this framework. So how was our proposal received? So Joelle and I spoke about our ideas at various conferences and seminars. Most people were polite and showed interest. And a few highly regarded scientists, such as Gilman and Zumino, stated that our proposal was potentially very important. Yet our work was largely ignored. Why? I believe the answer lies in the sociology of the profession at the time. Relativists who thought about black holes, the geometry of the universe, etc., had no use for quantum theory. It was far removed from anything of interest to them. Particle theorists who were interested in understanding phenomena that could be observed in current or future accelerators had no interest in gravity. There was a lot of interest in supersymmetry, but not in gravity. It was far removed from anything of interest to them. Now, both groups of scientists were correct in their opinions, of course, and therefore the two communities were completely disjoint. And a proposal that would bridge this gap had very few takers. It took a decade for this to change, but when it did, it happened very suddenly. So now let's talk about supersymmetry in 10 dimensions. In 1976, Liazzi, Shirk, and Olive proposed a projection of the RNS string spectrum, both for bosons and fermions, the GSO projection, that removed roughly half the states, including the tachyon. I didn't mention this earlier, but the spectrum that we had both in 26 dimensions and in 10 dimensions had one particle with negative mass squared. And such a particle would travel faster than the speed of light. It's a tachyon. So, so this GSO projection eliminates the tachyon from the spectrum, as well as lots of other things. And they showed that after the projection, the number of bosons and fermions is equal at every mass level. And this was compelling evidence for 10-dimensional space-time supersymmetry of the GSO projection, of the GSO projected theory. But it wasn't a proof. Just having an equal number of bosons and fermions doesn't mean that they're related by a symmetry. Supersymmetry is necessary for consistency because the spectrum contains a massless gravitino. And the gravitino is the gauge particle for supersymmetry, and that wouldn't make sense unless they were connected by a symmetry. So the 10-dimensional spacetime supersymmetry proposed by GSO in 1976 is distinct from the two-dimensional world-sheet supersymmetry identified by Gervais and Tsuchida in 1971. They're completely different things, even though both of them are supersymmetries. And they're both relevant to what I've been talking about. So the GSO projection is required for consistency. It ensures that the theory has supersymmetry in 10-dimensional Minkowski spacetime. However, it is important to note that this symmetry can be broken when the extra dimensions are compactified. And how it's broken depends on the details of the geometry of the compact extra dimensions. So once you have the theory of gravity, it's perfectly sensible to imagine that some of the dimensions curled up to form some sort of compact space. The only requirement is that it be consistent with the equations of motion. But since you're dealing with a theory that has to do with the geometry of spacetime, there are lots of possibilities. So in 1978, Hervé, Julia, and Shirk discovered a supergravity theory in 11 dimensions. So this is not a string theory. It just contains three fields. It's a field theory. So you have basically Einstein's graviton, except it's written in 11 dimensions, but it's the same kind of formula. And then the fields, which are the gauge fields for the supersymmetry of the gravitino fields. And to get everything straight, this theory needs a third field, which is a three-form tensor field. So a mu nu rho, which is the total antisymmetry, and has a four-form field strength. Now, this 11-dimensional supergravity they wrote down is a very beautiful theory. It's a brilliant observation of theirs. But being a quantum or being a field theory and not a string theory, obviously has severe ultraviolet divergences. So even though it's a nice classical theory, you certainly cannot make quantum mechanical sense of it as it stands. So a good question was whether it might be a low energy approximation to a consistent quantum field. And this question was answered in the affirmative, but it took a long time because they did this in 1978, and the question was answered in 1995 by Adam Wharton, who named the quantum theory M theory. So this 11-dimensional supergravity is just a low energy approximation to M theory. So in 1979, Michael Green and I began a collaboration, and the initial goal of our collaboration was to understand the 10-dimensional space-time supersymmetry of the GSO projected RNS string theory, and which we then named superstring theory. Uh, so, um, as I mentioned earlier, just having equal number of bosons and fermions doesn't mean it's supersymmetric. There have to be explicit transformations with all the right properties relating bosonic fields and the fermionic fields. So this was a challenging problem, and whenever we worked on that, so whenever possible, we also collaborated with Lars Spring. Now, Joel Scherk tragically died in May 1980. He was less than 40 years old at that time. Otherwise, he undoubtedly would have been a collaborator in the work that I'll be describing, and he would have been a major contributor. Uh, Green and I formulated what we call type 1, type 2A, and type 2B superstring theories. So we had this GSO projected 10-dimensional string theory, but there were a lot of details that hadn't been explained carefully. And and when explained carefully, we realized it was really three different theories that we could get out of it, which we gave these three names. We proved the 10-dimensional space-time supersymmetry of the spectrum and interaction in each case. So the theories with a 2 in them rather than a 1 have twice as many supersymmetries. So the type 1 theory has one supersymmetry, which in 10 dimensions has a supersymmetry spinner in 10 dimensions and 16 components. So this is, in a sense, 16 supersymmetries, and the 32 in each of these two cases. 32 is always the maximum possible amount of supersymmetry in any dimension. We computed various tree and one-loop amplitudes and elucidated their properties. We formulated superstring field theory and the Lycombe gauge for two of the theories, the type 1 and type 2B. And we introduced a new world-sheet formalism that made the 10-dimensional space-time supersymmetry manifest. Okay, I'm running a little long, but I'm near the end. So, is it okay if I take 5 more minutes?
Yes, yes,
Okay.
that's fine. Yes,
Okay. So,
please.
so it's essential for the consistency of the quantum theory. The local symmetries, such as gauge symmetries and local Lorentz invariants of the tree-level classical theory, are not broken by quantum corrections. And such symmetry-destroying quantum corrections are called anomalies, and they potentially occur at one loop level in parity-violating theories. In other words, theories that are not invariant on your mirror reflection. So the standard model is an excellent example of a parity-violating theory in which various such anomalies beautifully cancel. If one ignored the quarks or the leptons, the quantum theory would be inconsistent. But when both are included, their anomalies can cancel. So the standard model satisfies this requirement of anomaly cancellation. So the question is, what's going on in the case of string theory? So we had these three string theories: type 1, type 2A, 2B. Two more would be discovered the following year. So the type 2A theory is parity conserving, so there's no issue, and therefore it's anomaly free. However, the real world is parity violating, so it can't possibly be realistic. The type 2B theory is parity violating, and in 1983, Alvarez Gomez and Witten proved that all of its local gravitational anomalies cancel. And more recently, more subtle potential anomalies have also been shown to cancel. Anomalies whose existence we didn't even contemplate back in the 1980s. However, in 1983, it was unclear how one could get anything at all realistic out of this theory. That would change in 1996 when Vafa introduced a clever method to construct type 2B solutions that he named S theory. So anyway, for these reasons, we focused our attention on the type 1 superstring theory. Classically, it's a parity violating theory, but it's defined for any orthogonal or symplectic gauge group. And there are two worldsheet topologies that contribute to the gauge anomalies. One is a cylinder, like we discussed earlier, and the other is a Möbius strip. So we discovered what Michael and I, by doing the explicit calculations, found is that the two contributions can cancel, but only if you choose the right gauge group. And that gauge group turned out to be SO32. So we had an infinite, up until that point, we had an arbitrary symplectic or orthogonal gauge group. And now out of those two times infinity possibilities, only one gave the anomaly cancellation. Any other choice gives a theory that is inconsistent at the quantum level. We confirmed this result by an analysis of the low energy effective field theory. And in this setting, we could also analyze gravitational and mixed anomalies. And it all worked beautifully for SO32. When I say SO32, that's a little imprecise. It's right. The algebra, if you want to be precise about the group, it's spin 32, mod Z2. We also discovered that the anomalies could cancel for a second gauge group, namely E8 times E8, which also has 496 dimensions in rank equal to 16. But we did not know a superstring theory with this gauge group. But it was plausible that one should exist, and we set out to find it. Within a few months, Gross, Harvey, Martinick, and Rome introduced the heterotic string for both gauge groups. So after 10 years on our own, we no longer had the luxury of working leisurely without worrying about the competition. The subjects had suddenly taken off, and following the anomaly cancellation result, and that may not be the E8 theory. Shortly after that, Candile, Horowitz, Strominger, and Witten introduced a specific type of compactification called, they named Calabi-Yau compactification for the 6 extra dimensions. And applied to the E8 times E8 heterotic string theory, they showed that this kind of compactification of the extra dimensions could give 4-dimensional theories with many realistic features. And in those days, one emphasized what worked, but nowadays I think it's better to emphasize what doesn't work. And well, they were clearly on the right track. We don't yet have anything that's exactly right. So let me conclude. The history of string theory is one of unification of particles and forces, of particles and theorists and relativists, of math and physics. It's been an exciting journey. It's still going strong. There are several well-known examples of lucky experimental discoveries, but string theory is a very rare example of a lucky discovery in theoretical physics. Witten has remarked that string theory is the 21st century that happened to be discovered in the 20th century, which I thought was kind of a clever thing to say. The second superstring revolution occurred a decade after the first one in the mid-1990s. Important results concern new dualities, M theory, black hole entropy, F theory. I've alluded to some of these things already. Also, the ADS-CFT holographic duality discovered in 1997 was very important, but I didn't have time to try to do it. The current research directions include new types of symmetries, something called the Swampland program, celestial holography, a possible micron scale dark dimension. Let me conclude by saying that my current thinking is that cosmology might be a more fertile ground for experimental or an observational confirmation of string theory than particle physics. I've only come around to that point of view recently, but especially with the famous global tension that you've heard about from Wendy Friedman, I think that's that indication that there's something fundamental to be explained, and string theory might be able to provide the way to do that. And I'm not, that's just speculation on my part. So let me conclude there. Thank you.
Thank you, Professor John. It was wonderful. It was amazing. It was like a very complete crash course in string theory, starting all the way from QED and QCD. I was making notes all the time. Point it was difficult to keep up, but it was really nice to know everything. the kinematics, relativity, you went all the way to then, the 26 dimensions, 10 dimensions, superstring, supersymmetry. I mean, I can keep going on, but I hope everyone was paying close attention to that. So thank you so much. It was really beautiful. I enjoyed the lecture very much myself, being a student of QED. It was really wonderful to hear this from yourself. So I myself have multiple questions, but I'll just take this privilege liberty to ask you. And start with my question first. As you also beautifully concluded, I like the statement that the string theory is a theory of 21st century, which was discovered in 20th. So my question is, string theory achieves this remarkable theoretical consistencies and unification, but yet it lacks some direct experimental test. So, what do you think, in your view, that what gives us confidence that we are on the right path, or do you see any potential experimental test in your future?
Yes. So there was a period when people were hopeful that supersymmetry particles would be discovered at the LHC, and that would give us useful hints that could guide us to a more detailed string theory. Uh, but there's nothing that we understand that says that the scale of supersymmetry breaking should be accessible at the LHC. Any possibility all the way up to the Planck scale is conceivable, and so it hasn't shown up experimentally, and I'm pessimistic that it will. So, so as I indicated at the very end of my talk, is that I'm becoming more the that that string theory might be able to make some significant contribution to cosmology. I'm not the first person to say this. There are people working on this, and uh, it's the the famous Hubble tension, uh, where you where the work of Wendy Friedman and her friends gives one value, and the study of the CMB gives a different value. Uh, the For the Hubble constant, it's a strong
Mhm.
indication that the cosmological constant is a constant. It's it's evolving, and uh, so it hasn't been done, but it seems possible to me. One could find a string theory framework in which one can just figure out how the cosmological constant should vary, how it should be non-constant, and
Mm.
uh, perhaps be enlightening.
Yeah.
That's just speculation. It could be wrong, of course.
Mm. Yeah. Thank you so much for answering that beautifully. So I'd like to take some questions. So the first question is, what kind of discrete symmetries one can expect to be spontaneously broken in the early universe as per string theory? Does string theory has any criteria like renormalization for any kind of loop calculation? So there are three questions actually. There are a lot. Maybe you could just choose which one to answer. And the third one is, under which continuous symmetry can be expected, which can unify gravity with other interactions?
So anything involving cosmology, even though I'm keen to learn more about it, I don't feel confident to say more about. So I don't really feel qualified to answer the third question. And so string theory does not have ultraviolet divergences, so you don't need renormalization. So the
Mm.
loops always the different higher loop amplitudes have regions where the integrals converge. Uh, and so there's no renormalization involved. Uh, so that's it. That's a
Mm.
interesting fact.
Yes, thank you. Maybe we can take another question. Can you go to next? Yeah, okay, yeah. So there's a question from Sumit Tiwari, who is from Indian Institute of Technology, Bhubaneswar. Is asking if you were a graduate student starting your physics career today, would you still choose
Yeah,
to focus on string theory, or is there another unsolved problem in physics that you would equally find compelling?
right. So, as you know, I didn't start out with the idea of doing string theory. It just through the sequence of events that I described, that's where I landed. Uh, the there's no doubt that string theory is going to be around for a long time, but it's completely unclear how long it'll take to connect it up to the real world in a convincing way. That could happen tomorrow, and it could take many decades. Uh, so, I don't feel particularly qualified to tell other people what they should do. I think you should figure
Definitely.
that out by yourself.
Yeah. I think they're more interested in knowing if there is some some unsolved big problem that you see that might be
Well, I
potentially.
mentioned these issues in cosmology that seem interesting to me right now.
Mhm. Yeah. Thank you. Now
I,
you
one
can
thing I didn't talk
post.
about, although I alluded to it, is this dark dimension. It's an idea due to
Mhm.
Hoffa at Harvard, and I think that's extremely interesting too. But I didn't have
Mhm.
time to describe it.
Yeah. Thank you. There's a question from Rajesh, who's a consultant and learning mate. He says, you mentioned that string theory necessarily incorporates gravity. Could you elaborate on what makes gravity emerge so naturally in this framework, unlike other quantum field
Yeah,
theories?
right. Uh, yeah, we didn't set out to do it. We were trying to, as I told you, we were trying to describe a strong nuclear force, and boom, it was there. So it was this crazy thing that Lovelace discovered when we had this cylinder diagram, which had an, which we were thinking of as a one loop open string amplitude, but it became, you have this open string closed string duality where that same diagram can be viewed as a closed string going from one boundary to the other. And that's the closed string is the one whose modes, including graviton. So, so just by starting with a theory of things that weren't gravity, we found the theory has gravity. So we were particle physicists, we weren't relativists, and so that was just forced on us by the math. It wasn't what we
Mhm.
set out to do.
Yes. Thank you. Um, Maybe then I go to next question. The next question is from Dr. Roshan. It says, before Lovelace's result, no one seriously considered dimensions beyond four. What was the reaction in the community when 26 dimensions became unavoidable? Was there any resistance?
Well, I mean, clearly it was unrealistic, and uh, I mean, I think my feeling at the time was this is a nice kind of theory. Maybe there's one for which you get four dimensions. Uh, and so we tried to get another theory that turned out to have 10 dimensions. And as I said, at that time, I was saying, well, maybe our next theory will have four dimensions. But right now, after all these years, there aren't other string theories found. I mean, there are details about the theories I described, which can be called different sub-theories, but basically I described the basic kinds of theories that there are. Uh, so the thing is that when you make a quantum theory of strings, you get gravity whether or not you want to.
Mhm. Yes. Yeah, thank you. Maybe we just take one last question, keeping in mind the time. A question from Ruthvik. He says string theory initially lost relevance after the success of QCD, but later re-emerged as a framework for quantum gravity and unification. Looking back, what do you think allowed string theory to survive that period? And what lesson does that hold for how we evaluate new theoretical ideas today?
Yeah, I mean that was certainly one of the themes of what I was trying to convey. That in 1974, Shirk and I realized that even though we'd set out to describe the strong nuclear force, we had a theory of gravity. And so we don't need, and we don't need a new theory of the strong nuclear force because we've already got QCD, which is perfectly fine. So, so we could have done what most people did, which is go work on QCD and the other topics I mentioned, or take string theory seriously, but that means talking about gravity because that's what it gives.
Uh, Wonderful. Thank you so much, Professor Jones. It was really remarkable, very inspiring, and very good to hear all this from you directly. Because in regard of limited time, we would like to stop our Q&A session here. But we really appreciate you joining us and deliberating this lecture at your time. And thank you so much.